An introduction to special relativity. A woman standing on the ground sees a car approaching from her right and a train from her left. She sees the train pass at 100 km an hour and the car at 50 km an hour. These measurements are with respect to the ground frame of reference. But we could also view this from the car driver's perspective. If he's travelling at a constant speed relative to the ground and the train, then he could imagine that his car is stationary and everything else that's moving. This is the car frame of reference. When the driver sees the train coming towards him at 150 km an hour, while the woman and everything else on the ground is approaching at 50 km an hour. And in the same way, we could view the situation from the kid's perspective on the train. That's the train frame of reference. The car will be travelling towards the train at 150 km an hour, while everything on the ground will be approaching at 100 km an hour. These concepts of relative motion, rather than absolute, date back to Galileo in the 16th century and were developed further by Isaac Newton in his studies of the motion of objects. So Einstein used these principles in the first of his two postulates. It can be called the principle of relativity or the laws of physics postulate, and it says two things. First, all inertial frames are equivalent. Inertial means constant relative velocity between the frames. In other words, no acceleration. He was stating that there is no absolute frame of reference. You can choose any frame to make measurements from and assume that that frame is at rest. Second, the laws of physics apply equally in all frames. So if you're travelling on a train at constant speed relative to some other reference frame, then the motion of an object inside the train will be the same as if the train were at rest, no matter how fast the train is moving. But Einstein developed his theory from two postulates. So what is postulate 2, why did he consider it, and why was it revolutionary at the time? To answer that question, let's start off by imagining a boy on a stationary train. He shoots a paintball from one end to the other. As usual with special relativity, we want to compare events between frames. So we want to know how measurements in the train frame of reference translate to the ground frame. Of course, the train is stationary. Then any measurements of time, distance or speed in the train frame will be the same in the ground frame. But what about when the train is moving relative to the ground? We can see in this experiment that the paintball must cover more distance in the ground frame if it hits the wall of the train at the same time. And if the elapsed time is the same between the two frames, then the paintball must be travelling faster in the ground frame. So the speed of the paintball in the train frame equals the speed of the paintball relative to the gun. This is because the gun itself is moving with the train. Inside the train, it doesn't matter whether the train is at rest or moving really fast as long as it's moving with constant speed. But the speed of the paintball in the ground frame is the speed of the paintball plus the speed of the train relative to the ground. But what if it's a beam of light rather than a paintball? Of course, because we're dealing with light, we have to imagine the train is travelling really fast. But even no such train exists in reality, we can still imagine a hypothetical one. That's how Einstein conducted his thought experiments. The principles of classical mechanics suggested that the beam of light would hit the wall of the train in the same time elapsed in each reference frame. And then that would mean that the speed of light would be added to the speed of the train relative to the ground. This was the belief of scientists in the mid-19th century. But in 1864, James Clerk Maxwell showed that an electromagnetic wave, such as light, should travel at the same speed for all frames of reference, no matter what the relative speed is between them. This was a real watershed moment that was about to turn science on its head. Einstein made Maxwell's discovery in his second postulate, the speed of light postulate, that stated simply that the speed of light in a vacuum is the same in all inertial frames, approximately 300 kilometers a second. He then set about working to discover what these two postulates together really meant. Einstein thought about light travelling in two reference frames and deduced that at no time could the light beam be ahead in either frame, so that when the light hits the wall of the train in the train frame, it is still only part of the way in the ground frame. Einstein realised that the light beam in the ground frame would not hit the wall of the train until some time later. But Einstein also knew from the work of other scientists, including Hendrik Lorentz, that when reference frames move relative to each other, another phenomenon occurs, called length contraction, which acts in the direction of the relative motion. Although the concept was developed within the field of electromagnetism, Einstein realised that it could be applied to moving objects in general. So Einstein used the length contracted train in the ground frame to calculate where the light beam would be when it hit the wall of the train in the train frame. And then by calculating how much further the light beam had to travel, he was able to calculate the difference in elapsed time between the frames. Einstein had successfully demonstrated and quantified time dilation. To see time dilation in action, let's imagine we have a train moving really fast, relative to the ground, in this case 87% of the speed of light. At this speed, we'll have a time dilation factor of 2, so events in the train frame will take twice as long in the ground frame. And if time is multiplied by a factor of 2, then the length of the train in the ground frame will be divided by a factor of 2. So the length of the train in the ground frame will be halved. And a third effect will occur, called loss of simultaneity, which means that synchronous events that are separated by some distance in one frame will not be synchronous in another frame. So when all three of the effects are working together, the actions start to look quite a bit different in the ground frame. But recall Einstein's first postulate that all inertial frames are equivalent. This means that we have the choice to say that the train is moving and the ground is at rest. Or we can say that the train is at rest and it's the ground and everything on it that's whizzing by in the opposite direction. And so, we will observe similar effects in the train frame. At the same relative speed, a car moving at normal speed on the ground will be squashed into the train frame to half its length and only cover half the distance in twice the time. The effects are non-linear and get much stronger as the relative speed approaches the speed of light. The strength of the effect is called the Lorentz factor, or simply gamma. Imagine we have an event on the train that takes 10 seconds, as measured within the train. The measured length of the train in its own frame is called the proper length. We want to investigate how relative speed between the train and the ground affects the time and length in the ground frame. At low speeds, we don't need to worry about gamma, as it's so small we would barely notice any difference in between the frames, even up to 10% of the speed of light, which is over 100 million kilometers an hour. So let's increase the relative speed. At 42% of the speed of light, gamma is 1.1, so the length will be reduced about 10% and time dilated by 10%. Moving up to 87% of the speed of light, as we saw earlier, this gives a gamma factor of 2. So the train length is halved and the elapsed time is doubled. At 98% of the speed of light, gamma equals 5. The paintball looks more like a pancake in the ground frame and takes 50 seconds to reach the train wall. And what about if we had a relative speed that equaled the speed of light? Well, that's not possible for an object with mass, but if we could, then the train would simply disappear into the ground frame and time would be frozen. We hoped you enjoyed our introduction to special relativity. Thanks for watching, and check for our new videos coming soon.